Hello AP Physics, Nicole here, teaching you another AP problem. Today we're going to be looking at the 2003 AP Physics B, Form B, and we're going to be doing question number 5. So if you look at this question, you'll see that there is a PV diagram on top, and it shows a cycle, and also note that the cycle is in the shape of a triangle. That will be helpful later when we have to calculate work. Okay, so let's begin. The question asks, 1 mole of an ideal gas, that's important because that means that we'll be able to use the ideal gas law, is taken around the cycle A to B to C to A as shown in the PV diagram above. So it starts at A, goes to B, goes to C, and then back down to A. Part A asks us to calculate the temperature of the gas at point A. So let's just move to an empty space, and we can calculate the temperature. So since they told us that this was an ideal gas, we'll be able to use the ideal gas law. So we know the ideal gas law to be PV equals nRT, or some people call it perv nerd. So then all we have to do is simply plug in the values that they gave us. Now, they technically didn't give us any numbers, but if we look on the diagram, we'll see that the scales on the axes give us all the numbers that we need. So we're going to do pressure, and since we're looking at point A, pressure is going to be 200 newtons per meter squared times the volume at point A, which is going to be 20 meters cubed. And that's equal to N, which is the number of moles, which is just 1, times R, which is our constant of 8.31 joules per mole Kelvin, and then T is what we are looking for. So, when we multiply everything together and put it into our calculator, we should get that the temperature at point A is equal to 481.35 Kelvin. Make sure that all of your temperatures are in degrees Kelvin because all these thermodynamic questions do not use Celsius. Okay, now if we zoom out to part B, part B asks us to calculate the net work, so the total amount of work done on the gas during one complete cycle. So if we look at our diagram, like I said before, take note that it is a triangle, and we know that work is just equal to the area. So in this case, the area of a triangle is 1/2 base times height. So if we get a blank area of space to do our work in, so part B, we can know that work is equal to 1/2 base times height, and then work is equal to 1/2 the base, which is going to be 60 meters cubed minus 20 meters cubed, that's going to be the base, times 400 newtons per meter squared minus 200 newtons per meter squared. That's going to be the height. And all I did was look at the graph to get those values. So we're thinking about the base, which is going to be the change in volume, and the height is going to be the change in pressure. So plug that into your calculator, multiply everything together, and you should get 4,000 joules. And that is part B. Part C asks us, is heat added or removed from the gas during one complete cycle? Well, the answer is that heat is removed. In a closed system, we know that it's cyclic, so delta U is equal to 0. And that's according to the first law of thermodynamics. Therefore, work is already calculated for us before. We had that work was equal to 4,000 joules. Now, here in part C, if we do delta U is equal to Q plus W, we know that delta U crosses out. So then we have Q is equal to a negative work. So then Q is just equal to negative 4,000 joules. So that's how we know that heat was removed. Okay. Part D asks us, after one complete cycle, is the initial energy of the gas, so initial energy, greater, less, or the same as before? So, we're thinking about the internal energy, and we see that on the graph. Let's just move up. It is cyclic. So since it's cyclic, there is no change in temperature. And since there's no change in temperature, there's also no change in internal energy, or delta U. So our answer here is going to be the same. And what we can write down is that since there is no change in delta T, so delta T equals 0, therefore delta U equals 0, so there's no change in internal energy, because it is cyclic. And then finally, down here at part E, they ask us, after one complete cycle, is the entropy of the gas greater, less, or the same as before? So entropy is a state of randomness. And now again, think, this process is cyclic. So because it's cyclic, it starts at one point, so it starts at A, and then when we go through the cycle, it ends at A again. So we're starting at the same point and ending at the same point, so all we're doing is going back to the beginning. So therefore, the entropy of the gas is going to be the same because it is cyclic. Okay, everyone, I hope this helped. If you have any more questions, feel free to ask. Have a great day.